Hello, honors physics students. Let's get started in your notes. If this were a regular class, this would be your do now. So in your notes, I want you to copy down this chart, 3 columns here. Type of field, middle column, what creates it, third column, what you use to test for it. And then you're going to pause the video and fill in as much as you can. You should have no problem filling in that middle column, but that last column may not be exactly sure what goes there, but as we go through it, it'll probably make a little more sense. Okay, so as we go through, there's a great review of the different types of fields we've seen throughout the year. Let's start with gravitational fields, and before we get into 2 columns there, let's just remind ourselves what the symbol is for gravitational fields. Go ahead and write down the symbol for gravitational field. I hope you didn't write down anything with an F, because of course, F is for force, and of course that's one of the reasons why we're going through this, is to remind you that force and field are just not the same thing. Anytime you're dealing with either one or the other, it really just makes sure you know which one we're dealing with. This is field, right? So the symbol for gravitational field is, of course, lowercase g. Because remember, the other name for gravitational field is acceleration due to gravity, which is why they get the same symbol. Okay, so what is it that creates a gravitational field? Well, yes, of course, the Earth does, but it's not just the Earth, right? Hopefully you've expanded your horizons to consider that really any mass creates a gravitational field. The Earth does, the Moon does, the Sun does, Mars does, you do. Remember, we actually talked about this in class. Every single object creates its own gravitational field, so any mass. Okay, so now for that third column. Let's say you are an astrophysicist, and it's your job to map out the gravitational field some location in space. You want to figure out its strength, its magnitude, and its direction. So the question is, what would you put there to test for it that would react to a gravitational field? Well, the idea is that anything else, any other mass, will react to the gravitational field. So the idea is that this first mass over here creates the field, this other mass reacts to it. It experiences the field, and of course then they really interact with each other. Really, that's the gravitational force. If the think about the equation, F sub g equals capital G m1 m2 over r squared. So one object creates the field, the other object interacts with that field, together they interact with each other. Okay, so now we go on to electric field. What's the symbol for electric field? Go ahead and write it down. Of course, it's capital E. And what is it that creates an electric field? Well, it's anything with a charge, but if you go back to the way we first described it back in electrostatics, we say it's any object with net charge, right? There's some objects that intrinsically have a charge, like a proton or electron, but there's all sorts of other objects that can attain a net charge by means of either charging by friction, or charging by contact, or charging by induction, whatever it is, like a balloon. You rub it on your head, it attains a net charge, then it creates an electric field. Okay, so let's say you're in the lab, and it's your job to map out the electric field in some region of the lab. What could you use to test for it? What would you put there? Okay, yes, I know the ideal is a positive test charge. That's how all of our electric fields are drawn in the directions assumed it's a positive test charge. But what if you don't have positive charges? What if all you have are negative charges? Will it not work? Of course it'll work, so you can put it there. What if you don't even have, like tiny objects? What if you don't have a store of protons or electrons? If you rub a balloon on your hair and let it go, will it react? Of course it will, right? So really, what you use to test for it is just another object with net charge. Anything that has a net charge will interact with the field produced by the first. So again, this object produces the field, it creates the field, this other object experiences the field, and then they interact with each other. If these were both point charges, we use Coulomb's law. F sub E equals K, big Q, little q, over R squared, right? And so the idea is that they interact with each other. Alright, so now magnetic field. What's our symbol for magnetic field? Right, capital B. Okay, so bonus question. Do you remember, without looking it up, what does capital B actually stand for? Yeah, magnetic flux density. I'm really not going to worry about that, the differences between the two. For all intents and purposes, this is magnetic field. So, what is it that creates a magnetic field? I hope you didn't overthink this one. Of course, it's a magnet, right? A magnet creates a magnetic field. Great. Okay, so let's say you're in the lab, and it's your job to map out the magnetic field in some region of space. What could you use to test for it? Well, I wonder what it could possibly be. Oh, right, another magnet, right? And of course, you've seen in videos, really, you could use a compass, because a compass needle is a tiny magnet that's free to spin around, and it reacts to another field. So this object creates the field, this other object experiences the field, and then they interact with each other. Now, there is something else that you can put in this column that will react to magnetic fields. What you saw in the videos the other day, when they were showing the magnet affecting the motion of the dot on the oscilloscope. Remember, the dot is really just a whole bunch of electrons that were moving, hitting the screen, causing the screen to light up. And so when those electrons are moving, they also react to this external magnetic field. So what else could you use to test for a magnetic field? Moving charges. When charges are moving in a magnetic field, they experience magnetic force, which means they're reacting to it, and you can use that to test for the strength and direction of a magnetic field. Fantastic. Okay, so let's go over some homework questions here. Let's look in the textbook in conceptual question number 2. Can a constant magnetic field set a proton at rest into motion? Explain your answer. And as I always encourage you to do, we should always be looking at an equation. So we're talking about a proton, which is a really, really tiny object, right? It's a point charge. So of course we have the equation F sub m equals QVB sine theta. We're not using ILB sine theta because we don't have a current. We don't have a wire with current. We're dealing with an individual point charge, and that's what the equation tells us to use, QVB sine theta. Okay, so the proton's at rest, right? So V equals 0. And to get into motion, that means the motion's going to change, which means there has to be an acceleration. So clearly, of course, no, there's no way it can work, right? If V equals 0, the magnetic force is 0. That's how the equation works. And then from sigma F equals ma, if the sigma F is the only force, there can be no change in motion because there's going to be no net force. So of course it cannot. Now an electric field can, right? You put a point charge in an electric field over the any charge in an electric field and it experiences an electrostatic force which has nothing to do with velocity. So here's a big difference between electric fields and magnetic fields. Let's look at the other conceptual question here, number 21. All right, so we have this picture here. This is the electron beam. If you weren't quite sure, it's this lit up beam over here, and there's something creating a magnetic field because the beam is deflecting downwards. And the question is, what's the direction of the magnetic field? So again, we're dealing with electrons, which are point charges. We're thinking about equations, and we're thinking about like the right-hand rule. That would be a good thing to look at here. So here's a picture of me doing the right-hand rule along with the picture. So I've got the charges, which are moving to the right. They're being shot to the right in the presence of the magnetic field. So here's my pointer finger. And then, in this case, it's sort of like right-hand rule in reverse. We did a problem like this before, where we know they're deflected downward, so I stick my thumb out, try to stick it out all the way here, to point to the bottom of the page, or downward in the frame of reference of this. And then you just curl your middle finger, whichever way is comfortable. In this case, it should be out of the page. And so in this case, the direction of the magnetic field is out of the page. Or is it? Did you catch the trick? I hope you did, because remember I told you there's only one trick, and you're going to see it over and over, and don't let yourself get fooled by it, because these are electrons. Electrons have negative charges. Remember, we do the right-hand rule assuming that our pointer finger is pointing the direction of the motion of positive charges, and these are not positive charges. So what do? You flip your answer, right? So if this says that the field should be pointing out of the page, that means the field is really pointing into the page. There are other ways to do it. You can say that a negative charge moving to the right is like a positive charge moving to the left, so you flip your whole hand around. Or, of course, you could use your left hand. I don't like to use my left hand. I always want to use my right hand, but if you choose to do so, okay. Just remember that you have to look out for these tricks. And this is pretty much the only trick when there's a negative charge. All right, letter B. What would happen to the beam if the magnetic field were reversed in direction? Well, if you change something, then you change your answers. In this case, of course, it would be just deflected upwards. So instead of the beam looking like this, the beam would be deflected upwards. So we flip the direction of the magnetic field.